So you have now Jakob to talk about the zeta vacuum.
Thanks so much. Thanks so much for putting together this wonderful workshop and for inviting me to talk here. I was here 4 years ago, approximately, for a similar kind of workshop, and it was great. So I have high hopes for this. It's great timing for me because this is the modular stabilization section, and we have some upcoming work that I'm very excited about, which is about the zeta vacua, but it also, of course, involves modular stabilization, so it works out. Yes, the title is the zeta vacua at leading order. I will tell you exactly what that means. And it's based on upcoming work together with Naomi Gendler, Lee McAllister, Richard Nally, and Andreas Schaffner. But I should also emphasize that it's one piece in the puzzle of a bigger picture that we've been starting to put together in a longer series of work that has crucially involved Mehmet Demirtas, Menki Kim, and Andres Rios-Tescan as well. And Menki is also here, so he deserves a lot of credit for this. So let's start. Okay, let me give you the upshot right away before going into any technicalities. I will show you the first concrete examples of the zeta vacua along the lines that were envisioned by Kacu, Kalosh, Linde, and Trivedi 20 years ago. And I will also give you right away perhaps the most important caveat to this, namely our vacua will live to leading order in the string loop in alpha prime expansion in type 2B string theory. Although we're also including some known corrections to this. But of course, these we don't know all corrections, so these will be potentially vulnerable to corrections that we don't know. And I will comment on this a little bit in the end. Okay. Here's the plan. I'll do a brief motivation. Then I'll introduce or remind you of the various components that go into the KKLT scenario, and then we'll actually go and try to accomplish all of these things. First, I'll review how we found scale-separated KKLT anti-de Sitter vacua that are supersymmetric, and then I'll go on to the new work, which is to get uplifted versions of these that form the Sitter vacua. And then, as promised, I'll talk a little bit about corrections, and I'll conclude. Okay, let's do some motivation. Of course, there's a common goal to pretty much all of us here that we would like to study the imprint of quantum gravity at observable low energy scales, and there's many ways to approach this that I think we'll see at this workshop. One possible avenue is to construct and study sort of semi-realistic cosmologies and models of particle physics and string theory, and well, that's interesting because one might hope to learn about the UV origin of some of the exponential hierarchies that we find in the standard model of particle physics and cosmology from such solutions. And of course, the most famous such and most extreme such hierarchy problem is the cosmological constant problem that Thomas already mentioned in his review talk. And so this will be the centerpiece of this talk as well. Now, there's a caveat to this. The tuning of the cosmological constant in our world is not technically natural, and therefore, even if you can construct a solution that features the observed hierarchy of scales, we're not going to be able to control this unless we can compute order hundreds of loops, well, to a hundredth order in the loop expansion or something like that. Of course, we can't do that. So we can't protect a cosmological hierarchy in our computation if we assume a realistic SUSY breaking scale above the TV scale. However, we can still study a toy version of this of the cosmological constant problem, which I'll call the supersymmetric CC problem, by finding explicit vacua of F-term potentials that you find in string compactifications, i.e., you try to find solutions that have small flux superpotential and F terms that satisfy no particular tuning with respect to the gravitino mass. So in this way, you can hope to construct controlled ADS4 and de Sitter 4 vacua, even though the SUSY breaking scale will not be realistic. And note here, there's no particular distinction between ADS and DS here. Of course, supersymmetric ones will always be ADS, but in terms of control, there's no big difference. Okay, so that's as far as the motivation goes. And now I'd like to introduce, well, refresh everybody's memory on the KKLT scenario. Okay, 20 years ago, KKLT proposed a recipe for constructing a de Sitter vacuum in type 2B string theory. And it's a complicated recipe involving a long list of ingredients. One starts with a Calabi-Yau 3-fold X, compactifies type 2B string theory in it, but also mods out by an orientifold projection of O3-O7 type. One chooses 3-form fluxes that yield a very small flux superpotential W0. One has to find somehow sufficiently generic D3 instanton correction to the superpotential. One has to find an F-term vacuum for the Kähler moduli, which on general grounds one expects to exist if this point is satisfied, but one still has to actually go down and do it. Then in the final step, one has to find or construct a tuned warped throat region in the Calabi-Yau that can host a metastable anti-D3 brane uplift, and the hierarchy of scales of the throat has to be tuned to align with the size of the F-term potential. So we're going to try to do all of this, but first let me give you some a little bit more technical details on what's generally required here. Of course, we start with any Calabi-Yau 3-fold X. Type 2B string theory on it will give a 40n equals to 2 compactification, and then dividing by an O3-O7 orientifold defined by some holomorphic involution of a Calabi-Yau with fixed points at dimension 0 and 4 will give you 40n equals to 1 effective supergravity with chiral multiplets given by the axodilaton tau, H11 plus Kähler moduli, H1 minus complex structure moduli, and we'll consider the special case where, oh, you can't see it, H1 minus and H1 plus are equal to 0, so then these are the only chiral multiplets. Okay, then one has to go and find flux vacua in such orientifold compactifications, i.e. one starts with the Gukow-Waffer-Witten flux superpotential given in terms of 3-form fluxes F3 and H3 and the holomorphic volume form on the Calabi-Yau. So this will depend on the axodilaton and the complex structure moduli, not on the Kähler moduli. And then, if one assumes that there exists some VEF of these moduli such that the corresponding F terms are 0, then one can integrate out these moduli and start attempting to solve the F terms of the Kähler moduli. Okay, how does one do that? Without any quantum corrections, one cannot. The no-scale structure tells you that there are no F-term vacua of the Kähler moduli at finite distance. However, Witten showed, as in 1996, that the 3 instantons wrapped on rigid orientifold invariant and holomorphic force cycles will contribute to the superpotential, an exponential term in the Kähler moduli. And similarly, condensing gauge groups on 7 branes will also correct the superpotential with a slightly different coefficient in the exponent. And assuming that there are at least H11 such corrections here, one expects that Kähler moduli are stabilized at VEVs that are logarithmically large when W0, the flux superpotential VEV, is small. So control over the alpha prime expansion then requires that the flux superpotential is in this sense exponentially small. Okay, here, and this is if these assumptions are so if one indeed finds the corresponding instanton corrections in a single modulus toy example, this is the famous potential one finds in that's plotted in the original KKLT paper. One finds an ADS minimum that's supersymmetric. Now, of course, we're interested in de Sitter vacua, and for this, they also came up with a nice idea. If one assumes that there's a warped Reynolds-Sondrum throat that has this tuned hierarchy of scales, then the SUSY breaking potential of a warped metastable anti-D3 brane will change the scalar potential from this to this. So a supersymmetric ADS minimum will become a metastable de Sitter minimum if this tuning has the right order 1 coefficients in it. Okay, now thus far the fantasy, the recipe, but now let's actually try to do this. And so I'll start with constructing KKLT, supersymmetric KKLT Vacua based on work from a couple years ago, and then later I'll uplift. Okay, so our playground for the geometric part will be the Kreuzer-Skarke data set of 4D reflexive polytopes. Here are the 2D versions of those. Triangulating these defines 4D toric varieties. They are generic anti-canonical hypersurfaces, are Calabi-Yau. And one can study these very effectively with the software package SQL tools. And in recent years, we've made a lot of progress in studying Calabi-Yaus in this framework here. And by now, we can study even the most generic and complicated Calabi-Yaus in this list. Now, another piece that one needs is orientifold. And it turns out that given an arbitrary reflexive polytope delta, one can enumerate all the O3, O7 orientifold projections and efficiently compute the data of the corresponding O-planes in terms of basic combinatorial data of the polytope. So this is a paper that I had earlier this year. I don't have time for the details, but if you're interested, take a look. And as a special subclass of these orientifolds exists that have H1 minus equal to 0 and H21 plus also equal to 0. And these arise from a special class of polytopes that are a 3D toy version being depicted here. They sort of have 3 layers, the middle layer containing the origin. So one can efficiently find these and construct these orientifolds. And so now we have in hand a Calabi-Yau X, some holomorphic orientifold of it. And now we would like to find flux Vacua with small flux superpotential. So what do? For computational feasibility, we look at the large complex structure region of complex structure modular space, where we can compute the Calabi-Yau periods systematically order by order in the large volume expansion, including both perturbative and non-perturbative pieces. And then it turns out that for special ansatz in fluxes, that is described by 2 H2 one-dimensional vectors M and K, the flux superpotential takes a special form. It's a quadratic homogeneous piece and instanton corrections to it. So exponentially small at large complex structure. Now, if these fluxes that determine the perturbative piece here satisfy in addition a Diophantine equation, so this can be written as this equation here in terms of a rational vector P that's defined by the fluxes in this way, then the polynomial part will vanish identically along a one-dimensional sublocus modular space where the complex structure moduli and the exodilaton satisfy a relation given in terms of this constant vector P. And also the F terms of the F term of this will be identically 0. So now then one can integrate out all directions except the one-dimensional light modulus, parameterized in terms of the string coupling tau. And the effective superpotential for this is then naturally exponentially small because it's just given by the exponential corrections. For example, for explicit Calabi-Yau orientifold with H1 plus equal to 113 and 5 complex structure moduli, we found a effective superpotential that takes this form. It's a sort of racetrack superpotential with the polynomial hierarchy and the coefficients that's set out front that are GV. Yes?
Sorry, I just want to understand. Is this where you say you step away from the original KKLT proposal? I might misunderstand because
if you want, yeah.
The superpotential is too small by flux numbers. Here, these are decent numbers.
Oh, sorry. This is still the entire thing here, including the exponential corrections, comes from the flux superpotential. It's just from the mirror perspective, these are instantons. So they are exponentially small, but they are still classical from the type 2b side. Yeah. So that's why why we can compute them. They're just given in terms of GV invariance of the mirror. Yeah. So indeed, the coefficients out front here are Gupa-Kummer-Waffa invariance, and for further slightly tuned fluxes, one finds that the exponents are closely aligned. So these are real examples that one finds from real orientifolds and real flux choices. So one finds very closely aligned exponents, and then the racetrack superpotential has an F-term solution given in terms of the ratio of these of the polynomial terms outside here to a high power 29 that comes from the closeness of the exponents here, and that turns out to be about 10 to the minus 61. So this is what we found in this paper. So that's as far as the complex structure sector is concerned. But you might say, so far we've only stabilized 6 moduli, the 5 complex structure moduli and the exodilaton tau, but we've completely ignored the Kähler sector. We just held them fixed by hand. So one has to go further, but in the above example, one can show that Witten's criterion for non-vanishing D3 instanton contribution to the superpotential is satisfied for actually 114 complex divisors. So the corrected superpotential takes the form of the classical one plus these ED3 instanton corrections here, and given in terms of homology classes of the corresponding cycles. And on general grounds, one expects an isolated KKLT-like minimum for the complex structure moduli. But that's just a genericity assumption. One has to actually go and find the VEV in Kähler modular space. So with this, one has to stabilize 113 moduli in a complicated F-term potential. So one might say that's hard, and it is slightly non-trivial, but one can do it. And here's a strategy for how to do that. That pretty much always is successful. One first defines an initial guess given by simply setting all the terms in the superpotential roughly equal. And then one defines some arbitrary Kalbiau from some triangulation of the reference polytope, and chooses some arbitrary point in the Kähler cone as a starting point. Now, if this point here exists, then you can find it by flowing across a straight line through modular space from the starting point expressed in sort of dual divisor coordinates and going to this point here. The reason is that the divisor coordinates take values in a convex cone. It's called the cone of movable curves. So if it exists, the entire path also exists. So one has to flow along this path, and one can do this. However, it's still a little non-trivial because along the way, at large H11, one will encounter order hundreds of flop transitions along the way. So here's a picture of a two-dimensional cross-section of the extended Kähler cone of the Kalbiau with largest Hodge number 491 in the Kreuzer-Skarke database, and each little dot here represents one Kähler cone. So one has to do this, but one can. It's just one has to discretize the path, and you can think about this as a discretized BPS attractor flow. And so that's what's supposed to be written here. So one can do this, and lo and behold, once you identify the actual vacuum point, actually it's not T star, it's the actual point where once you find this point, then you're close enough to, it turns out that you're close enough to the actual F-term solution that you can find the true F-term solution by using relatively simple-minded methods like Newton's method. I'm not implying that Newton was simple-minded, but this works. And lo and behold, the mass spectrum at the vacuum point is free of tachyons, and here's the mass spectrum. Note that this is expressed in units of the ADS scale, so all eigenvalues are actually pretty large. Okay, so far was just the supersymmetric ADS part, and now let's tweak this to get de Sitter solutions. How am I doing on time? Oh, okay. Mm-hmm. That's right, yeah. Yeah, so for the one I showed you, I just set them all to 1. But one can show that in these examples, they're just numbers. So this is Mankey has done a lot of work on this. They are not functions of the complex structure model, so these are just some order 1 numbers. But you can show, and we've done that by just sprinkling them randomly, that the VEB essentially doesn't move. And the reason is that what really matters is how small W naught is. So unless you make one of the coefficients as small as W naught, which is, in this case is 10 to the minus 61, you will essentially change nothing. Yeah. Okay. So for an uplift, we have to construct a warped throat with fluxes M and K given on conifold cycles, so we have to find, and so in terms of these fluxes, the conifold complex structure will be exponentially small. So one has to find flux numbers that this indeed turns out to be exponentially small, and one then has to find solutions that where a warp throat hierarchy matches the one of the atom potential. Now, that is a little non-trivial because for a single anti-D3 brane, the uplift to de Sitter has to be tuned in this. So this is the parametric form. Numerically, one finds this. Z and W0 appear here, but then there's also a relatively small numerical factor in front here. You have volumes of the Calabi-Yau and its mirror in the denominator. So you have to find solutions where both of these numbers are pretty small, and this one is much smaller than W0 because of these conspiring numerical factors here. So one has to do this, and but one can, and so in order to do this, one goes to a facet of the large complex structure cone where a conifold becomes singular, and in this region, one can compute the Calabi-Yau period systematically, order by order, in the conifold complex structure, and so you can expand in this form, and the famous logarithmic branch cut of the conifold superpotential appears in the order in the order Z term here, and we can compute all the relevant terms here. So then one has to solve a slightly adapted Diophantine equations and flux numbers in order to make this term here exponentially small, but one can do this. And similarly, the complex structure moduli associated to the bulk. So these are, you can think about as a parametrization of the facet of the LCS cone that we're considering. You get a similar kind of a relation between complex structure moduli and the dilaton. And in terms of such a solution, one then stabilizes the conifold Z at this value here, which contains the generic K over M here, but also contains computable threshold correction. So we actually know what the VEP here is. Okay. Okay. But that's not all. One also needs to ensure that the strongly warped throat has a metastable anti-D3 brane uplift, and so according to the classic computation by Katri, Pearson, and Verlinde, one has to have one of the flux numbers greater than 12. And for control over the alpha prime expansion, one also needs that this other factor GS times this flux number is bigger than 1. And so when you do this, requiring an uplift to the Sitter limits the amount of computational control you can have quite severely. You have an exponentially small number here, which is given in terms of, which is bounded by the D3 charge in the throat. In order to make this, to make Z exponentially small, you need a large D3 charge. And if you want to make the curvature of the throat small and the string coupling weak, you need a lot of charge. So it turns out that for the largest D3 tadpole you can find in KS, which is 252, and reasonable control parameters of like 20%, and W0 of 10 to the minus 2, you can do this, but you can't do much better. So now let's put all of this together. So far we've done everything separately. At least I've told you how to do this. And now let's actually do it. So we start with about 200,000 polytopes in KS in a suitable range of H21 where we can do all the computations. Then we restrict to favorable polytopes that admit an endfold where the other Hodge numbers H1 minus H1 plus are equal to 0. So we drop by a factor of 100. We want a large D3 charge for which we set an ad hoc bound of 75. We want enough rigid divisors. We're down to 300, so roughly 400 polytopes. Then we want that suitable conifold limits exist that don't intersect with O-planes. And then now we just find around 250 Calabi-Yaus. And from these, we can construct perturbatively flat vacua, PFVs, with conifolds, and we find around 150 million of these. So that's a large number, but we're not done. We actually want that solutions with small flux superpotential and conifolds exist from these, and now we're down to about 90 million. Now, the final point you can't see, but there's around 25,000 vacua where the D3 charge is, of the fluxes is just so it admits for a single anti-D3 brane. And I have 1 minute left. and with a flux number m of the KS solution is bigger than 12. So it's consistent with a single meta-disabled anti-D3 brane. And here are statistics for for W naught and conifold Z, and you see that finding appropriately aligned values is merely a matter of statistics. And here is a concrete example. This is the F3 flux, this is the H3 flux, and you can see this is the conifold flux here. It's above 12. GS is about 10%, 8%, 9%. W naught is 10⁻². The curvature parameter of the throat is about 1.4. Not impressively large, but it is bigger than 1. And here's the scalar potential before the uplift and after the uplift. So you can see it brings you to the zitter, and you get a barrier towards decompactification. Okay. It's also tachyon-free. Here's the mass spectrum in ADS units before the uplift. Here's the mass spectrum in units of Hubble after the uplift. So you find similar kind of spectrum as before. And now, of course, the question is, how controlled is this? Okay, I don't have time anymore, so I'm just gonna say that there's a question of alpha prime corrections at the bottom of the throat that has been studied by Heber, Kashrai, and Venkin recently, and so there's a question over if the metastability survives these alpha prime corrections. My take on this is that whether or not metastable vacua exists at GSM of order 1 is not conclusive, so more has to be done. The string couplings are not extremely small. Einstein frame cycle bumps are not impressively large, so there's a bit of a question there as well. And if you make simple ansatz basically similar to Berghack pi here for corrections, one finds order 20 to 30% correction. So these are not extremely well controlled, but I see this as good motivation to study these further. And so I'm just going to flash the outlook here, and thank you for your attention.
Thank you. Jaco, questions?
Thank you. That is
He's for the Zoom more than for us.
okay. So, well, very nice result. But how genetic is to get a not perturbative superpotential for each of the KM?
This is good question. This is extremely generic at large H11. It's not very generic at small H11. And the reason is that if you have polytopes with large H11 have a lot of points interior to faces, and these points interior to two faces, which correspond to most of the 4-cycle classes, they are always rigid. So those will always contribute, and then the ones inside of one faces for favorable polytopes will also always contribute, and then there's only one more. You only need one vertex divisor to also be rigid in order to succeed. So this is very, very generic.
So if I remember correctly, in this construction of the symmetric area spectrum, the construction model that is like extremely light, right? Order W naught.
Parametrically, there's one light complex structure model that has massive order W naught. That's right.
And so I was wondering if you then apply Suzy break and drop it to simple, whether you also check that modulus will not find a run away.
Yeah. So this is what I showed you here is with respect to. Actually, I'm not sure if this what I showed here might just be the back direction on the Cannon model here. But yeah, so the back direction is pretty small.
If it's very light, I mean,
yeah.
You don't know much about what's happening. So.
Well, we know we know how the uplift potential depends on the string coupling, and that is what parameterizes the light direction. So this is something one can compute.
Could you have all 3 or 7 planes, also D7 branes, of course, on the object?
Yeah.
And the instance house that you use do not intersect that O plane?
The instantons intersect the O planes in P1s.
In P1. Oh,
Yes.
very good.
Yes. Yeah. So if there were hygienists, then there would be a question of exos element.
Okay, maybe one final many questions. But Ana Maria, let's take two more questions, and then yeah, he surprised us with the de Sitter type too. So because we have a discussion on the Sitter, so maybe some of the questions can be postponed to them.
When you said do all at once, you still do first the compactification, the stabilization of the structure. You find it to zero, then you find the stabilization of the K-level moduli. But you don't do all at once. I mean, like complex structure moduli and K-level moduli all at once.
Yeah, so this is all at once. Yeah, I was just showing you the logical steps of first isolating the individual components. But yeah, in the end, you just have to solve all the F-time conditions for all the moduli, and then you find the
values of W you are getting W not are not sufficiently small to be viable phenomenologically. There is any hope to use it to a minus 12, or I don't know what to mean.
Sorry, what do you mean by it's not phenomenologically viable?
Well, the idea is that W naught should be of order of the Suzy breaking masses or something, or the close to the electroweak scale.
Well, Suzy breaking
Otherwise,
at the high scale.
If you break supersymmetry only slightly below the stream scale or the Planck scale.
Yeah, so as I said before, like we can't find solutions that have the C of order what we observe while keeping the Suzy breaking scale large and retaining computation control. You would have to compute the e to the k factor, for instance, to 100 loops or something like that. So no, we can't do that. So these are toy models. These are not actually realistic cosmology.
Okay, short question.
Well, I've been trying for a while.
Yeah.
I was just wondering if there's any sort of effect where you might have a beastly Witten cancellation between your different instanton contributions in a given class. Have you checked that, or is it excluded? Or?
I think this is excluded. We thought about this somewhat extensively. So the D3 branes here all have. I mean, these are rigid 4 cycles. They only have a single representative. So I don't think there's any room for cancellation.
Okay. Let's postpone the discussions to the questions to some of the discussion sessions. I mean, thanks.